Okay, hello everyone. Today we will finish this chapter, discrete random variables and their probability distributions. We will talk about the moment generating distributions and then Chebyshev inequality. Okay, let's solve example 3.23. Find the moment generating function mt for a Poisson distribution, Poisson distributed random variable with mean lambda. Okay, and by the definition of mt, it is expected value of e to ty, and from the definition of expected value of a function of random variable, it can be represented as this, and this py from the definition of the Poisson distribution, it is written as this, and from here we can write it as y equals 0 to infinity and y factorial, and from here this is actually e to t y, and this e to t y times lambda y, this one becomes et lambda y, so et lambda y, and we have expected value of minus lambda. Okay, and from here, actually this part does not depend on y, so this part can go out. And for this part, and actually there's two ways to solve this part. The first one is to use the probability sum of py equals 0 for Poisson distribution, and the other way is the uh, using the Taylor expansion of e to x, which is sum of y equals 0 to infinity y factorial x to y. Okay, so let's use the first one first. The first one, if we are using this one, let's say so this one becomes e to the minus lambda sum of y equals 0 to infinity and y factorial e to the t lambda to y, and here if some random variable follow Poisson distribution with et lambda, then this will hold from y equals 0 to infinity and y factorial et lambda to y and and e to the minus et lambda. The sum of this will 1. So we multiply e to the minus et lambda and also multiply e to the minus et lambda plus et lambda, because this times this equals 1, so this one is written as we can move this one outside, so which is e to minus lambda times e to et lambda, and now this part is 1, and now this part is sum of 1, and the solution is e to lambda et minus 1. Okay, this is the using the first way, and the other way is using this one. So here y equal the sum of y equals 0 to infinity and y factorial et y y, and actually here since e to x is this thing, and here x from here x is this thing, so here this is actually e to et lambda. So we can directly put this one here, and then we get this one from, so this is from method 2, and this is from method 1. You can use anything 1 or 2 from to get the solution of this one. Okay. Let's move on to example 3.24. Use the moment generating function of example before, example 3.23 and theorem 3.12 to find the mean mu and variance sigma square for the Poisson random variable. So from the previous example, we derived the moment generating function for Poisson distribution, which is this. And by using theorem 3.12, if we get the first derivative of this moment generating function and put 0 here, we get the first the first moment, which is the expected value of y, and if we derive it 2 times and put 0, we get the second moment. And so if we calculate this one and this one, this is mu, and we can calculate sigma square equals e to the y square minus e y square to get the sigma squares. Okay, so so let's solve these two. What would be the first moment? The first derivative of moment is that if we derive this one, it is e to the lambda e t minus 1 and lambda e t minus 1, this one, and if we get the derivative of this thing, is that e to the lambda e t minus 1, and this is lambda et. Okay, and if we put 0 here, if t is 0, then m prime 0 is this is e to 0 is 1, y it's 1 minus 1 is 0, e to 0 is 1, so this one is lambda. Okay, what would be the two derivative of moment generating function? So we derive this 2 times, and before we do that, actually this is lambda times e to lambda et minus lambda plus t. Okay, we derive this to the derivative of that is lambda e to lambda e t minus lambda plus t, and the derivative of this thing, lambda e t minus lambda plus t derivative, and with respect to t, so this is lambda e t minus lambda plus t, and times lambda e t plus 1. Okay, so this is the second derivative of that, and put 0 here, and then we get e to 0, which is 1, lambda plus 1, so this one goes to lambda plus 1, and here e to 0 is 1, and t is 0, lambda minus lambda is 0, so e to 0 is 1, so this one becomes lambda times lambda plus 1. Okay, so the e to y square is lambda square plus lambda, and e to expected of y is lambda, and so mu is lambda, and the sigma square is expected value of y square minus expected value of y square, and this is actually lambda square plus lambda for this, and minus ey, which is lambda and lambda square, so this one cancels and this is lambda. So as a result, the mean mu is lambda, and the sigma square variance is again lambda for the Poisson distribution. The next example is 3.25. Suppose that y is a random variable with moment generating function. MIT is this one. What is the distribution of y? And actually, this one, it looks very similar to the moment generating function of Poisson distribution. Actually, the from the previous example, moment generating function of Poisson distribution, it was like e to the lambda et minus 1. And actually, this is very important property, that is there is one-to-one correspond between moment generating function and the probability distribution. So it's uniquely determined. So because the moment generating functions are unique, um, if our moment generating function looks like this, then the variable y, this follows the Poisson distribution with lambda 3.2. So if we know that the moment generating function of Poisson distribution looks like this, then we can identify the distribution of y. Since the moment generating function of y is this one, and this is moment generating function for Poisson distribution, so the random variable y follows Poisson distribution with parameter lambda 3.2. And so this is proof for this example. Okay, this is end of chapter 3.9, and homeworks are these. Okay, chapter 3.11 is about Chebyshev's theorem, and the Chebyshev's theorem is that let y be a random variable with mean mu and finite variance sigma square, then for any constant k is greater than 0, any of these two hold, the probability of absolute value of y minus mu is less than k sigma. The probability of this is greater than or equal to 1 minus 1 over k square, or probability of absolute value of y minus mu is greater than or equal to k sigma. The probability of this thing is less than or equal to 1 over k square. And actually, the domain here, y minus mu is so let's say from this interval, this point is y minus mu, and this is sigma k sigma bound, and the set here is defined on here, and the set here is defined on outside. So sum of these two probability is 1. So this is 1 minus this is 1 minus this. So if you prove any of these inequality, then you can get the other. So let's just prove this one. And before we prove this one, let's define the new random variable z as y minus mu divided by sigma. Then what we'll know is that expected value of z is 0 and expected value of z square, which is ez square minus ez, which is sigma square. The variance, this is 1. Okay, so, and also let's define one more random variable, which is 1 absolute value of z is greater than or equal to k. And this random variable have value 1 on the set, on this set, and have 0 otherwise. Okay, so this is our new random variable, and then you can see this equation like k times 1 z is greater than, absolute value of z is greater than or equal to k. This one is less than or equal to absolute value of z on the set here. Why this is true? So this is random variable, and random variable is defined on set S. And it is mapped to the real. Let's say this axis represent the real axis, and this part is the set S, and our random variable is defined on this set. And let's say this part is the set. Absolute value of z is greater than or equal to k. And for this function, it is k times 1, so it is k on this area. And however, for the random variable, this thing is absolute value of z, and absolute value of z are greater than k. So the random variable absolute value of z is greater than k. So we can check the inequality here. Absolute value of z is greater than equal to k times this random variable. So we can see this equation, and also we can check that the k square function of this thing, k square, if we write it this way, absolute value of z, k, and it is greater than absolute value of z square, and that's because z square is again greater than or equal to k square. So this thing also holds. For this case, here is k square, and from this domain, z square is greater than k square. So for k square times 1, this thing, this one holds. And let's take expectation on left side and right side. So expected value of k square times 1, z is greater than k, and so this part is actually k square, and from the definition of expectation, the definition of expectation is sum of y equals y times py, and actually this y equals 1 on this set. So this is 1 on this set. Probability of absolute value of z is greater than or equal to k. On this set, it's 1, and 0 on the other set. So expected value of the left hand side is k squared times p probability of absolute value of z is greater than or equal to k. And what about right hand side? The right hand side is just expected value of absolute value of z squared on again the same set. And actually this is less than or equal to expected value of z squared. Why is this true? Here z squared is always greater than 0. So this part is actually expected value of z squared on z is greater than k, and plus expected value of z squared defined on z is less than k, and this part is also greater than 0. So we can see this inequality. And expected value of z squared, this is 1. So this is proof of this second part. Here what we found is let's say this is and this is k squared probability of absolute value of z is greater than or equal to k, and this is less than or equal to 1. So this one is actually this one. So this is the proof for Chebyshev theorem. Let's move on to example 3.28. The number of customers per day at a sale counter Y has been observed for a long period of time and found to have mean 20 and standard deviation 2. The probability distribution of Y is not known. Okay, so EY is 20 and variance of Y is 2 square. What can be said about the probability that tomorrow Y will be greater than 16 but less than 24? And from the Chebyshev inequality, we know this. We can know the lower bound of probability of this. And what we want to know is Y is greater than 16 and less than 24. Okay, so our mu is 20. Our mu is 20 minus k sigma, which is 2k. And from here, 20 plus 2k. Then from here, to make this 16, k equals 2. K equals 2. Then we this domain is this one, and so this is 1 minus 1 over 2 square, and this is 3 over 4. Okay. Homework for 3.11 are these. And the homework from chapter 3, suggested problems, are these. Okay. And thank you.